Welcome to the next video of this tutorial. Here we will build our first model to predict the energy consumption. We have already seen how Pearson correlation coefficient can help us selecting relevant variables that can help us to predict the energy consumption. There are other correlation coefficient approaches, for example, Spearman rank order correlation coefficient, you can see if hour and month is correlated with the energy consumption, but it gives the similar result, that is higher the correlation, better it performs to predict the energy consumption. So it is here just for your reference, you can have a look there. So let's consider the columns that will help us and relevant and with higher correlation values, and we remove other weather data that is maybe irrelevant. So we update the weather file with knmi updated is a new variable name, and knmi.loc location is actually we are defining which location we want to remove, and with this we are selecting all the rows, and this curly sign is actually to remove the columns that we define within this square bracket. And then we run this, we see the new data frame. Here Q is the global radiation and WF is the wind speed. So now we develop a machine learning regression model. In literature, the mostly practiced approaches are support vector machine and random forest. Random forest is fast in calculation, but in this tutorial we are going to cover both of these approaches, and it depends on the type of data set that we are working on, which model will perform better. So let's start with random forest. I start with the support vector machine, but before going to develop the model, we need to split the data set into two data sets. This is a training set and testing set. Here we are splitting it 80% and 20%. You can explore with 60% and 40% if you wish. So we first import this train test split from the library of sklearn.model selection. So what it does, that train test split is splitting the weather file and the energy data into x values and y values. And with test size we define 0.2, that means we have 80% of the training data and 20% for testing data. And random state equals to some number actually specifies every time we run this cell we are getting the same values for the training set and test set. So when we see how many we have in the training set, we see there are 21,000 rows. That means 80% of the entire data set. Well, and this way we cannot calculate, we need a flattened array. So to convert it into an array, we use this ravel, which is a numpy function which changes a two-dimensional array or a multi-dimensional array into a continuous flattened array. And this is how it looks like after we flatten it. The same way we transform the test data, and the flattened array we can later calculate it. So let's import the regression model, that is a support vector machine. We import support vector regressor. You can go through the documentation for further exploration, but I will explain that is required for this tutorial. Creating an instance, this is an object, that is SV regression. We define the model here with SVR and kernel equal to RBF. So what it does is there are different other kernels available, for example linear, polynomial, radial basis function or sigmoid. By default radial basis function is here, which is used in machine learning to find a non-linear regression line. So we use it. We have considered the default values here. And when we train the model into the training set, that is X train and Y train, which we splitted earlier, so here the model is trained with this line of code, and all these parameters which are default are we just continue with this. So what are these hyperparameters? For example, this epsilon is 0.1. It is actually the maximum error allowed in the function. We increase it, that means the error we are giving chance to increase. Then what is this C value here? So this C is the set, the tolerance for points which fall outside of the error boundary set by epsilon. And then what is the gamma value? Is scale. Scale is the default, that is equal to 1 by n features times x variable, but it actually influence of a single point on the model. Okay, so let's see what happens if we predict the energy based on the training set, and we get these arrays of data, that is the energy required. It is what we are predicting. So there is no way that we see these arrays and we see how it performed. So to understand the performance of the model, we can use the coefficient of determination, which is the regression score function R square, and we can also use the mean squared error values, which actually indicates the average distance of the best fit regression line to the observed values. So when we import these libraries from sklearn, then we run and print the R squared value, and we compare with the training set with the predicted set, and again we see is only 1.5% is the accuracy, and the error is 41. So we definitely don't want this little accuracy with our model. So let's see, why do we have this very low accuracy of our model? If we check the data frame, that we have column with the temperature, relative humidity, and we also have the column with the air velocity, which is very high compared to the other columns. So with the higher magnitude, it has more weight in the calculation. So we need to do the scaling to improve the model performance. There are several approaches to do the scaling. Let's check three most popular approaches. One is standard scaler, which standardizes the data to a range in which mean is equal to 0 and the standard deviation is 1. And mean mass scaler is it normalizes the data and brings the values between 0 and 1. And robust scaler is another scaler that standardizes the data, but it is more robust to outliers. So we generate the scaler with this SC1, 2 and 3, and we run this, and then we scaling the input data. So we again put new variable name x1, 2 and 3, and with this scaler we fit transform the updated weather file. So this fit transform is the function that actually scale the entire data frame of this weather file. Well, so these are the inputs, input data that we use to predict the output data, and we do not need to scale the output data because we have only one output, that is the energy value. If we have multiple output data, then we need to scale the output values as well. So how these scalars actually look like, we can plot it with the help of SNS library, and distribution plot with we see the standardized and normalized values, how they are spread between -2 and 2 and 0 to 1. And when we split again, with the training set and test set, we can see how these x1 values that we define for the standard scalar is performing. We just copy the same line of codes here and we see how it can predict accurately. So when we print the r-square value and the mean squared error, we see the performance improved very well, that 86.7%, and the error is also very less, which is 5.5. And we can also check the test set, that is 86.5%, and for the test set the error is also very less. So it is not overfitted or underfitted for the training set. That means if the test performance is much higher than the training data set performance, that means it is underfit. Or if the test set predicts lower than the prediction than the training set, then it is overfitting. Well, so we can compare with the min max scaling with the help of x2 and with the same line of codes, and we see the min max scalar is a bit lower, and with robust scaling it is also a bit lower compared to what we have found with the standard scalar. Right? So we can decide that standard scalar is much better. The same way we can then in our next videos we will see how we can improve our prediction performance further with other different techniques. Till then, have a nice day.